Hello, this is Discrete Maths 1081, Chapter 2, and we're going to have a look at question 18. This is really a bit of a mixture. It's got some number theory in it, and it's also about equivalence relations and equivalence classes. The number theory is pretty straightforward, so let me say a little bit about the idea of an equivalence relation. An equivalence relation is a way of generalising the equal sign. So if you think about the equal sign's got a number of properties. Every number equals itself, obviously. And if you say A equals B, then obviously you can conclude that B equals A. And if you've got A equals B, B equals C, then you can conclude that A equals C. So they're sort of basic properties, if you will, of the equal sign. And the idea of an equivalence relation is simply some new kind of relation that mimics or generalises or models itself on what happens with the equal sign. So here we're given an equivalence, we're given some sort of relation here that says two numbers in this set S are equivalent if and only if their squares are the same mod 5. Always in discrete maths, try and put the stuff into English. Two numbers are equivalent if and only if their squares are the same modulo 5. And the first thing is to prove this is an equivalence relation. So we have to prove each of these different parts of it. The fact that anything's equivalent to itself, technical name we use for that is we say the relation is reflexive. This says the relation is symmetric, and this says the relation is transitive. So keep those basic ideas of equals in mind, and then we come back to do this thing here. So clearly, any number when you square it gives you the same answer mod 5 as when you square the same number. And so that tells me that x twiddles x. And so we say this relation is reflexive. So that's the first one. So that's trying to copy this idea here. Now, if we say that x is related to y, then that means that x squared is congruent to y squared mod 5. And now all I want to do is turn it around. Well, that's clearly the same as saying that y squared is the same as x squared mod 5. And then by definition that says y twiddles x. So that says this relation is symmetric, is the word. And finally, if x twiddles y and y twiddles z, that tells me x squared is congruent to y squared and y squared is congruent to z squared mod 5. And then just using properties of congruence, that says if they're the same mod 5 and they're the same mod 5, then x squared and y squared are the same mod 5. And that tells me that x twiddles z. So that says that this is transitive, is the technical word. So we've proven that this relation is reflexive, symmetric, and transitive. And therefore, this symbol is an equivalence relation. So that's an equivalence relation. Now finally then, to get rid of this here, to get the equivalence classes, that simply means that you want to chop up this set S into some sets, some smaller sets, in which every element in each of those smaller sets is equivalent to every other element. So we're going to partition this set S up into such sets. And look, the easiest way of doing this here, I think, is just have a look at what the squares all look like modulo 5. So make up a little table. So 0 squared is 0, 1 squared is 1. I'll put up here mod 5 to save writing it. 2 squared is 4, 3 squared is 9, and 9 is the same as 4 mod 5. 4 squared is 16, which is the same as 1 mod 5. 5 squared is 0 mod 5. 6, by the way, is exactly the same as 1, so you haven't got to think too hard there. 6 squared is 1, 7's the same as 2, so that's 4, and 8 squared, 8's the same as 3, so that's 4. So by looking at the squares, so the equivalence classes for S are, well, 0 squared gives me 0, and I look down and see what else gives me 0. Well, 5 does. So they, and nothing else. So they belong to the first equivalence class. Look down here, I've got a 1, so 1 squared is 1. What else squares to 1? Well, 4 does, so 1 and 4 go into the same class. What else does? 6 does, so we put 6 there and nothing else. And finally, 2 and 3 both square to give 4, and so do 7 and 8. And so there are the 3 equivalence classes. Now notice 2 things about the equivalence classes. Firstly, if you take the union of these, you get 0, 1, 2, 3, 4, 5, 6, 7, 8. You get back to where you started from. And none of these have anything in common, so they are all disjoint. There's no element that belongs to more than one equivalence class. So the equivalence classes partition the set up into mutually disjoint sets whose union is the set S you started with. And that always happens with every equivalence set of equivalence classes. And so that's the end of the problem.